We ended the previous video in the middle of the proof of the following theorem. Theorem: if p is an odd prime, then nu of p is equal to p over 8 plus an error term, where the error is less than 1/4 square root of p plus 2. We had gotten to this equation and observed that we needed to bound the sum by 2 times the square root of p in order to complete the proof. In order to do that, we're going to define a new function s of m. First, notice that we can manipulate s of 1 to a more useful form. After factoring and shifting the index, we see that this is the expression that we need to bound in order to complete the proof. For us to do this, we're going to show that s of m has certain properties that we can use to estimate its value. First, we break the sum into two parts and use symmetry to help us to simplify it. We will rewrite the second sum by taking n prime equals p minus 1 minus n, and noting that as n runs from p plus 1 over 2 to p minus 1, n prime runs through the values 1 through p minus 1 over 2. After reducing modulo p, we can factor out the negative 1 in front of the n prime in the Legendre symbol and simplify the negative n prime squared term. Notice that when p is congruent to 3 modulo 4, we have that negative 1 on p is negative 1, so that s of m is equal to 0 in this case. This gives us a very tight bound on the error for these primes. We will now focus on the case where p is congruent to 1 modulo 4, which means that negative 1 on p is equal to 1. Because of this, we can combine the two sums together. This shows that s of m is always even, which is a fact that we'll come back to later, but it doesn't actually help us calculate its value. We are going to return to the original equation and show that s of m has a functional relationship with itself. Suppose k is an integer such that k is not congruent to 0 modulo p. Then k to the fourth on p is equal to 1, and we can multiply this through without changing the values. After using the multiplicative property of the Legendre symbols a couple times, we end up with a form that suggests a variable change. Let h equal kn, and notice that as n runs through all the values in a complete residue system modulo p, so does h. And this gives us the functional equation. Now suppose that j is a quadratic residue modulo p. Then there exists a c such that j is congruent to c squared mod p, and we will use this to evaluate another expression for s of 1. Notice that this implies that the absolute value of s of 1 is equal to the absolute value of s of j. Now suppose that L and L prime are quadratic non-residues modulo p. If g is a primitive root modulo p, then we must have that L and L prime are odd powers of g. Without loss of generality, we will assume that b is greater than or equal to a. Then we can let t equal g to the b minus a so that L prime is congruent to LT squared modulo p. We can apply the functional equation again to see that the absolute value of s of L is equal to the absolute value of s of L prime. What these two calculations show is that the size of s of m is only dependent upon whether m is a quadratic residue or non-residue modulo p. Therefore, since we know that there are p minus 1 over 2 quadratic residues and p minus 1 over 2 quadratic non-residues, we must have this equation. Before we launch into another series of manipulations, we want to note that s of 0 is equal to 0. With this fact established, we will manipulate the left side of the equation. We can add in the s of 0 term without changing the sum, and then after explicitly substituting in the formula for s of m, we can rewrite it like this. We can now apply a result from the previous section on the innermost sum. The next several steps are mostly simple rearrangements and substitutions. In the last step, we use the fact that p is congruent to 1 modulo 4 to conclude that both s squared and negative s squared are quadratic residues modulo p. When we substitute this back into the equation we were working with, we find that we get the result we've been seeking. This calculation also gives us an important corollary. Corollary: every prime p congruent to 1 modulo 4 is representable as the sum of two square integers. In fact, we even have an explicit formula for this. The only observation we need to make is that s of m is always even, which means that these quantities are always integers. This is the most technical proof for the entire class. You may have to watch this several times and pause for a while to work through the details of the long calculation in order to really understand all the bits and pieces that come together to make this proof work. Despite the level of technicality, this is a proof that you should be able to understand fully if you take the time to work through it.
Thank you for watching this video. I'm currently dabbling with the idea of creating more videos like these for my classes, and I welcome constructive comments that might help me make better videos in the future.